The biggest gift a physicist or astronomer can get is a set of completely fresh data that reveals something about the universe that we've never seen before. And data like this doesn't come often. New experiments and new telescopes are expensive and take years, if not decades, to develop. But this month, December of 2021, it's finally here. A brand new telescope, JWST. Later this month, JWST will be launched into space and will open the doors to lots of new understandings about the universe. In today's episode, we'll break down what's so new and exciting about this telescope and what kind of new scientific discoveries you should be looking forward to. You may be wondering what JWST stands for and why we're spelling out this kind of annoying acronym. So it stands for the James Webb Space Telescope. And James Webb was a NASA administrator between 1961 and 1968 who was very involved in the Apollo program. However, there's been a lot of controversy around the naming of this telescope after him because a lot of LGBTQ advocates have pointed out Webb's complicity in NASA's purging of LGBTQ individuals from their workforce in the 1960s. Despite these calls, NASA announced a few months ago that it would keep the James Webb Space Telescope name rather than changing it.
So it's our opinion here on Why This Universe that the anti-LGBTQ policies from the era in question of our nation's history were absolutely deplorable. And furthermore, if naming a telescope today after someone like James Webb makes any of our LGBTQ colleagues feel unwelcome or unsupported by the larger scientific community, then we should probably give the telescope a different name. With this in mind, we've decided that in this episode and in our day-to-day lives, we're going to refer to this telescope simply as JWST without making any reference to the name James Webb. This episode of Why This Universe is supported by Wondrium, formerly known as the Great Courses Plus. Wondrium is a subscription service that offers thousands of video and audio courses on a huge range of topics. I've personally been a big fan and regular consumer of Wondrium's content for the past 15 years or so. I've listened to dozens of their courses, including ones on history, philosophy, literature, math, and science. For me, it's like taking an intro-level university course on a subject you've always wanted to know more about, but without the big tuition fee, and all in the comfort of your own home or daily commute. One of my favorite courses offered by Wondrium is called Games People Play, which is all on the subject of game theory. Over 24 lectures, you'll learn about the structures of different kinds of abstract games and the strategies that follow from those structures. I knew a little bit about game theory before listening to the course, but by the end it had really clarified my thinking on different kinds of games, like the difference between zero-sum games and non-zero-sum games, and games that feature perfect or imperfect information. The course also talks about some of the applications of game theory to topics like economics, evolutionary biology, and even politics. So if you want to learn more about almost anything, check out Wondrium and give them a try.
You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago. Thinking back to my early childhood, I can remember being really excited about Christmas time. I loved all the candy and cookies and festivities, seeing my cousins, building snow forts, getting all the time off school, all that stuff. But probably, if I'm being honest, the thing I looked the most forward to were the presents. My brother and I would get up early on Christmas Day and we'd just sit by the door of our room. Our parents wouldn't let us come out until we got the call to come see what Santa brought us or whatever. The anticipation was almost as good as the presents themselves. Well, it seems that astronomers have been pretty good this year, these last few decades. And during this holiday season, they're going to get something they've been looking forward to for decades. I'm talking about this hugely anticipated telescope, the JWST, which is scheduled to be launched into space on December 22nd on board this heavy lift space launch vehicle operated by the European Space Agency called the Ariane 5. In many ways, JWST is the successor to the famous Hubble Space Telescope, which was deployed back in 1990, or 31 years ago. One of Hubble's greatest legacy, of course, is this collection of these glorious, colorful, vivid images of nebula and newly forming stars and distant galaxies.
If you haven't seen these images before, give Hubble images a Google image search. It'll be worth it.
For many people, both non-scientists and scientists, they looked at these images and it inspired with them a sense of wonder about our universe. There are probably even a lot of astronomers today who, when they were young and seeing these images, were inspired to pursue this career path. But these images were really only a small part of Hubble's larger scientific legacy. Over its mission, Hubble helped astronomers to better measure how fast our universe is expanding. It helped astronomers to study these supermassive black holes that inhabit the hearts of galaxies. It helped us to determine with greater accuracy the size and mass of the Milky Way galaxy. And it made it possible for us to study dwarf planets and other pretty small objects in the outer regions of our own solar system. The hope of the astronomical community is that JWST will be at least as impactful for the next generation of astronomers as Hubble was over the last 30 years to astronomy. And that's a very big, lofty goal, but one that I think we can realistically hope for. So once it's deployed into space, it'll take about 180 days or almost half a year for JWST to reach its final destination, a point in space known as L2.
So unlike the Hubble telescope, JWST is not going to just be in orbit around the Earth. So how does this work? If you plopped a telescope in most places in space, the gravity from the sun and the Earth and the other planets would all interact in a complicated way to slingshot that thing around, and it would probably leave our vicinity pretty quickly. But what Dan just called L2 is the label for a very special point in space, a Lagrange point. At points like these, the gravity from the Earth and the Sun work together so that the telescope can be parked there in a sort of stable orbit.
It's a place that lies along the line that connects the Earth and Sun, but it's about 1.5 million kilometers away from the Sun that the Earth is. So if you can kind of picture the solar system, draw a line straight from the Sun to the Earth, and then keep going another 1.5 million kilometers. That's where L2 is.
So JWST will be parked precisely at this L2 point.
It will trace along the Earth at keeping this 1.5 million kilometer distance, and it will always be on the opposite side of the Earth from the Sun, which will protect it from that nasty sunlight and allow it to stay cold and be this kind of perfect space telescope out there as the Earth and JWST system moves around the Sun.
Now, JWST is attempting to be much more sensitive than Hubble was, but in order to do this, it's important that the telescope itself doesn't get too hot. After all, things that are hot radiate light. Think about those heated coals glowing red in a fireplace. And even us humans radiate light. It's just in the form of heat that we can't see with our eyes. If a telescope is any bit hot, it'll also radiate light. And that's going to interfere with the light it's actually trying to see, the super faint light from very, very far away galaxies. So astronomers are taking lots of extra precautions to keep JWST as cold as possible.
It has this 5-layer sun shield that's about the size of a tennis court. It will kind of unfold in space. It's made of these high-tech materials, silicon, aluminum, and it's coated with this film called Kapton. And altogether, the mechanics of JWST and its sun shield should allow it to maintain a temperature below 50 degrees Kelvin, which is about 388 degrees below zero in Fahrenheit. And that will allow it to see things that a hotter telescope can never see. It really controls the kind of what we call thermal backgrounds that a telescope like this would experience. Let's take a minute to kind of describe the telescope to give you a visual image of what we're talking about. So, like a lot of telescopes, this thing relies on mirrors, but the mirrors kind of look exotic as well. So there's a big primary mirror, which is actually made up of 18 smaller mirror segments and hexagons. These mirrors are gold-plated beryllium, so they're not just normal glass or silvered glass or something. So it's this kind of exotic material.
It kind of looks like a honeycomb, for bees.
Yeah, right. You can picture all those hexagons that make up a honeycomb. It's kind of like that. Yeah, 18 of these, honeycomb segments.
Yeah, we're taking their design.
Yeah, bees have figured out space telescope design long before we did, I guess. So this big primary mirror made up of these 18 smaller mirrors is about 6.5 meters in diameter. So this is a really huge mirror for a space telescope. For example, Hubble's primary mirror, which we think of as being big, was only 2.4 meters in diameter. So in area, JWST's mirror is 7 times larger than Hubble's, making it able to collect 7 times as much light and information.
And you can just imagine how hard it is to get a mirror that big into space.
Along with this big primary mirror that collects the light, that mirror then reflects the light and focuses on the secondary mirror, which is where all the instruments collect the light and try to make these images. You should probably Google a picture of JWST to get a better picture of what you're looking at here. The size of a telescope's main or primary mirror is important because this determines how bright an object has to be in order for that telescope to see it. The bigger the mirror have, the fainter an object it can potentially detect. Also important is the telescope's angular resolution, which for JWST is about 0.1 arc seconds. So an arc second is 1/3600th of a degree. So this can see something that's 1/36,000th of a degree across, which is almost nothing. I noticed online somewhere they were saying you could resolve a penny with this telescope at a distance of 24 miles. So it's kind of just super high resolution. Between that and the overall size of its mirror makes it just an incredibly powerful device. So JWST has 4 separate instruments that it can use to collect and measure the light that is gathered by its mirrors. Whereas Hubble is mostly sensitive to light in the visible range, the same kind of light that our eyes can detect, JWST's instruments are designed to be most sensitive to light in the infrared range. More specifically, JWST will be able to detect light that has a wavelength in the range of about 900 nanometers, which is near the middle of the visible range, up to just over 28,000 nanometers or 28 microns, which is near the middle of the infrared. Infrared light is useful to astronomers because it can penetrate through dust clouds much more easily than visible light can. So if you're thinking about studying objects like newly forming planets or newly forming stars, these things are often clouded or surrounded by clouds of dust. If you point something like Hubble or another visible telescope at it, you basically just see a big cloud of dust. Just picture looking at a cloud in the sky. You can't see through it. But to a telescope that's looking at infrared light like JWST will, you'll be able to see right through that dust and see the heart of that star forming or planet forming region, allowing us to understand how these processes take place in a way that a visible telescope might not be able to teach us.
You can imagine that the image that it constructs compared to that of Hubble will have things that Hubble could not see.
Absolutely, yeah. Yeah, they're just different kinds of tools. They bring different kinds of information to the table. Every astronomer wants to be able to look at an object in every possible wavelength, which oftentimes you can't do. But this is going to provide us with a totally fresh and new look at some of the things that Hubble has already seen in the visible spectrum. So by detecting infrared light, JWST will also be able to see farther away and farther back in time than Hubble could. In part, this is because of infrared's light and its ability to penetrate through dust as it travels through the universe. But it's also because of this phenomena known as cosmological redshift. So as the universe expands, it stretches the wavelength of photons of light along with it. So if you start out with some light that has one wavelength, as the universe expands, that light will take on longer wavelengths and move from the visible range into the infrared range. So, for example, imagine that there's some star that was active when the universe was only 500 million years old. Maybe it radiates a bunch of visible light. And then by the time that light reaches us, some 13.3 billion years later, the wavelength of that same light will be 10 times longer, moving from the visible range into the infrared. This would be hard for Hubble to study, but it's perfectly suited for a telescope that works in the infrared like JWST. So one of the most powerful things that Hubble did, at least to a cosmologist like myself, is something called the Hubble Deep Field Project. So back in 1995, Hubble focused its attention. It just zoomed in on a tiny little patch of space about 2.6 arc minutes across. And it spent just 10 days focusing. It just pointed in that direction as long as it could. And this direction was chosen because there wasn't a whole lot of known stuff there. There weren't many stars or other objects to compete with. But as it looked farther and farther, slowly it started to detect distant stars and galaxies from way back in the universe's history, 500 million years or so after the Big Bang. These objects were too faint and distant to have ever been resolved by other telescopes, but Hubble could see them for the first time. And it really provided us with this important image of our universe when it was very young. In the same spirit, JWST is going to be able to do something similar, but even looking back farther in time and closer to the Big Bang, this really formative era of our universe's history, when galaxies had just begun to form, and the very first stars that ever existed in our universe were slowly forming at around that time. So for the first time, we're going to be able to get these pure images of this window of cosmic history during which the very first stars and galaxies were actually forming as early as only a couple 100 million years after the Big Bang. JWST is going to do more for astronomy and cosmology than we can realistically hope to talk about in this one episode of this podcast. But I want to focus in on at least a few of the areas that I think are the most exciting or among the most exciting things that this incredible telescope is going to do. So first of all, number one, JWST will be hugely important for studying objects known as active galaxies. All or at least all of the galaxies in our universe are thought to contain a supermassive black hole at their center. And most of these black holes aren't really doing very much. They're just kind of quiescent. They kind of sit around, things orbit around them. But other than that, they're not very exciting.
Right. They're not like sucking in the whole galaxy or anything.
Right. But in a small fraction of all galaxies, those black holes are sucking in material from their environment. Not the whole galaxy or anything, but the surrounding, gas and dust and stuff. And this heats that gas into dramatic temperatures, making it a big, giant source of X-rays. And in many cases, they create powerful jets of matter and energy that fire out along the kind of perpendicular axis of the galaxy. We call these galaxies active galaxies, and we call the black hole system in those galaxies active galactic nuclei. And you can imagine this is a hard thing to study because it creates all this complicated stuff that's hard to see through. But with a powerful infrared telescope like JWST, we should be able to see at the hearts of these objects, try to understand what's really going on, and try to understand these active galaxies and their nuclei and their black holes in a way that we haven't been able to understand before.
So here's to hoping that JWST's launch goes as expected later this month. At the time of posting this episode, the JWST launch date is set for December 24th at 7:20 p.m. Eastern Standard Time, right on Christmas Eve. If you want to follow along with live updates, you can follow at NASA Web on Twitter. That's at NASAWEBB. It's been a very hectic time for the scientists working on this launch, and there's a lot of anxiety circling. But if all goes as planned from here on out, it'll be a very exciting year for astronomy in 2022. Thank you so much for listening to Why This Universe. If you want to support us more and get access to some exclusive content like exclusive interview clips, Ask Me Anything episodes, the opportunity to ask us questions, and a free sticker, you should definitely join us on Patreon. You can find us at patreon.com/whythisuniverse, and we really appreciate all the support that we get through there. Today's episode was produced and edited by me, Shalma Wegsman. My co-host is Dan Hooper, a professor of astrophysics at the University of Chicago and Fermilab. He's also the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jake Kleinbaum. And Why This Universe is brought to you by the University of Chicago Podcast Network.
JD. It's really a tongue twister.
This is why they should have changed the name.